Okay, so there's no real textbook that talks about this. There is one by Warren and Wyatt. Organic synthesis, I think it's strategy and control. Strategy and control. That talks a bit about the extended enolate problem, but there isn't much that you can actually find that really highlights it, which is a shame because it's actually a really interesting problem in the questions that we're actually discussing in this course. So an extended enolate, at least that's what we're going to refer to it here. An extended enolate is what you might otherwise called as a dienolate. Yep. Dienolate. Okay, and I'm going to focus there on the diene part because, you know, there we have a diene. And then we have our olate, if you like. So an extended enolate is that compound in the middle, the dienolate, and it can be formed one of two ways. Well, we can deprotonate an alkene ester on the left at the alpha position, or we can deprotonate a conjugated system at the gamma position. Sorry, I'm being nonsense. There we go. There we go. Keep going all the way up. There we go. So the alpha and gamma positions are, of course, here and here. And in case you don't remember, the beta position is the one in between them. So the key question when you get a extended enolate is, of course, where is it going to react? Does it react much like a normal enolate at the alpha position, or does it go all the way down the conjugated chain and react at the gamma position? Well, it turns out that this is a classic example of kinetic versus thermodynamic control. The alpha carbon is actually the kinetically favored position. Okay, so we're under kinetic control if we want to get the alpha product. So, under kinetic conditions, it reacts with an electrophile like that. Now, there's a very good chance, however, that if you do get this as an intermediate, that under the conditions of the reaction, it will re-enolize. Okay. It is an unstable, unconjugated alkene. And it tends to move into conjugation. There are examples where it doesn't, but there's a lot of examples where it does. Ultimately, some kind of base can deprotonate, and then it reprotonates at the gamma position. Now, equilibration gives the conjugated product because that is ultimately more thermodynamically favorable overall. Now, alpha carbon is kinetically favored. The other kinetically favored position is for very hard electrophiles. Okay. Very hard electrophiles react kinetically at oxygen. So an example of a good hard electrophile, it would be something like trimethyl oxonium. Okay, and that reacts on the oxygen. However, thermodynamic alternatively, it reacts with silicon. That also reacts on oxygen, and that is broadly because silicon oxygen has a very strong bond. But reversible electrophiles will react at the gamma position. Blue. Nope. Reversible electrophiles usually react at gamma position. So, what do we mean by a reversible electrophile? Well, I will very shortly tell you. Key thing is that alkylation is pretty much irreversible. So, if you take the ester on the left here, and you treat that with LDA, it deprotonates. Well, to be honest, it deprotonates at either of these positions. There's no difference here. As soon as it's deprotonated, there's free rotation around that single bond. So either one, you couldn't really tell which one's which. And it does alkylation at the alpha position. So it reacts at alpha position. So initially that gives us the monobromide shown in the middle. 7th equivalent of LDA, of course, deprotonates at the same position. And then it cyclizes to give the cyclopentane. What we might consider a reversible electrophile would be something like an aldol, an aldehyde or a ketone. And the reaction then that we're doing is the aldol reaction. So you can use, under these circumstances, a strong base like LDA again. So we generate the same dienolate, and if it reacts with the aldehyde at the alpha position, well, if you do the work, that can work if you do the work up at minus 78 degrees. Okay. Let's minus 78 degrees C. is low enough to prevent equilibration. Okay, if there's no equilibrium, we are talking kinetic. Okay, but warmer temperatures result in reversibility. So it is thermodynamic control at that point. So I think that in this particular case, we also have something that really favors the reversibility, namely that if you do the reaction to these conditions, it can actually cyclize to give the lactone, which is going to be quite favorable. So both of these are actually very useful if we can get them to work. The issue here is, how do we control them? Well, we've already said that we've got thermodynamics and kinetics in operation. So essentially controlling conditions, controlling reagents should give us the option to get through to our desired products. So first of all, the Mukayama aldol reaction. And Mukayama aldol is an aldol reaction using silicon. Okay, so we treat this aldehyde with triethylamine and trimethylsilyl chloride, and we get the extended enolate. Okay, these are soft thermodynamic enolate formation conditions. Okay, so we get the dienolate, and it can then react with a good electrophile. So in the case that we've shown below, we've got a dimethyl acetal in the presence of a Lewis acid, which is titanium tetrachloride. The titanium tetrachloride coordinates to one of the methoxys, and the other methoxy kicks it out. Okay, so we generate this oxocarbenium ion. This is pretty reactive, sufficiently reactive for certain that the TMS enol ether will react with it, and it preferentially reacts at the gamma position. Okay, the TMS enol dienol ether is relatively unreactive. We need a very reactive electrophile for the reaction to work. So an aldehyde wouldn't be reactive enough on its own. That's why we have this acetal being used. Okay. The TMS enol ether reacts at the gamma position because we get a more stable cation formed. So from this intermediate, we can draw multiple resonance forms and that is therefore more stable than wrong way around. Pardon me. Okay, there's only one resonance form that you can draw in that one, whereas there are multiple that you can draw for the other one. So we actually generate a more stable intermediate if we do this reaction at the gamma position, which is what ends up being the rationale for this. So we react all the way at the gamma position, and upon deprotection of the TMS group, we end up with the aldehyde here. And we can then treat that with a base. We generate an extended enolate again. And we do an E1CB elimination to give the dienaldehyde, which would actually be relatively difficult to make by a lot of other methods. Okay, so that's easy enough. I hope you'll agree. Different, but relatively easy. Let's go for something a little bit more complicated. With the aldehyde, there was really only one place to deprotonate, here. But what if we were looking at a ketone? Well, now we could deprotonate at the gamma position, but we could also deprotonate at the alpha prime position. Okay, so now we've got multiple things that we need to think about. Do we deprotonate gamma to generate the extended enolate, or do we deprotonate at the alpha prime position to get the cross-conjugated enolate, which obviously reacts just like a normal enolate? Well, this all very much depends on the conditions. Hopefully you can imagine that this is a more stable, more conjugated product, anion. Okay, we can delocalize the electron density onto the alpha position or onto the gamma position, and of course onto the oxygen itself, which is the main contributor. With the cross-conjugated enolate, we can only delocalize it onto the alpha prime position. Okay, so it is delocalized over fewer atoms, and as a rough approximation, the fewer atoms an anion is delocalized over, the less stable it is. So a thermodynamic deprotonation is going to be deprotonation at the gamma position to generate the extended enolate. Deprotonation at the alpha prime position is not going to be thermodynamic, but it might be kinetic. And by might be, I mean it is. So if you treat the cyclohexenone shown below with LDA, strong kinetic base, you generate the cross-conjugated enolate, which you can then react selectively at the alpha prime position. You could also react it with trimethyl chloride to generate the diene shown on the right, which you can then use with for a Diels-Alder reaction or something. Now, LDA, if it's going to be a kinetic deprotonation, minus 78 degrees C. Okay, minus 78 should probably be like the sign that we're trying to do something kinetic rather than thermodynamic. Okay, so enols, enol ethers, pretty familiar. Other equivalents? Well, what about an enamine? Can we generate an dienamine, an extended enamine? Well, yes. The formation of an enamine is typically under thermodynamic control. So we can generate the gamma reacting dienamine relatively easily. And I said earlier that TMS chloride and triethylamine are soft, gentle thermodynamic enolization conditions, so they also give the TMS enol, the extended enolate. And we can use those to then generate more reactive systems if we need to. So if you take the TMS ether and you react it with methyl lithium, you get formation of tetramethylsilane and the enolate. So we can actually use a thermodynamic reagent to generate a more reactive system, which I think is cool. I think a lot of things are cool. So that all works nicely. And using these reagents, we can do a lot of standard ionic chemistry. However, a dienol or a dienamine is actually a very useful reagent that we could possibly use to do Diels-Alder type chemistry. So we use our thermodynamic conditions to generate the TMS enol ether. We can then do a pretty standard Diels-Alder reaction to give this product over here. Same kind of thing with the enamine. And here we're actually using a very extended dienophile as well. So there's quite a lot going on with this one. And it gives you the endo product. If we weren't trying to use the extended system, it might actually go through a different mechanism like we mentioned on Monday. But in addition to doing using extended enolate, we can also do the cross-conjugated to generate another enol system that puts the TMS group in a different location, and so we can actually produce a cyclic ketone. And in actual fact, we're doing this with one of the CDK projects that Lavleen described in her thesis. So that's useful. So the Bayliss-Hillman reaction. The Bayliss-Hillman reaction is almost related to this, in that it seems to give you the same product as would happen with the alpha position of an extended enolate. This is a nifty reaction. So, in the extended enolate case, what you would do is that you would take cyclohexenone, you react it with a base that gives you the thermodynamic enolate, and then it reacts under the kinetic conditions to give an aldol reaction, and then ideally under the conditions of the reaction it would then epimerize to give you the product shown here. However, there are cases where you couldn't do that because you couldn't form an enolate. So if you took this acrylate here, you couldn't do a deprotonation at the gamma position here because there is no gamma position. So how can you do an aldol type reaction to get the product here? Well, that's what the Bayliss-Hillman reaction does. Okay. This reaction occurs readily with amine, specifically tertiary amine and phosphine catalysis. What it does is that it generates an enolate in situ by doing a conjugate addition here. That enolate can then do the aldol reaction to give this intermediate, which by deprotonation, what happened? By proton transfer, we regenerate the enolate, which then does an E1CB reaction to give the product. And the phosphine catalyst back So we form the enolate by conjugate addition. And the phosphine is a catalyst because it can be regenerated and reused at the end of the reaction. Okay, so you often only use about 10%, though lower catalyst loadings are also possible. Most commonly, amines are actually used for this. Phosphorus often works slightly better, but can be more difficult to get rid of. And the classic amine that is used is actually Dabco. Okay. Dabco is actually a very, very, very cheap amine. Most simple amines are. But although it's very cheap, it's very good. It can actually be quite slow. So it's often used in stoichiometric amounts. It's often used in stoichiometric amounts to speed up the process. If you didn't use one equivalent, instead of taking 1 hour, that would probably take 24 hours, possibly even 48. It can be quite slow. Very annoying. Okay. Right. So that is the end of the extended enolate problem. And now we're doing relatively good time today, I'm glad to say. Now we're going to go on to a topic that fills a lot of people with horror, and it shouldn't, and that is radical chemistry. Okay. Radical reactions people are often very upset about, and I understand it because radicals are often taught about being these really reactive things that will react with any old thing, and there's no control because they are so reactive. This is not true. Okay, radicals really can be very selective, surprisingly selective, but they do react quite fast. So they're both fast and selective. That's a pretty good thing to happen. They are also very useful, not only because they're quite reactive, but they can do types of chemistry that are quite different to what you're used to seeing. And I will show you that, well, now. So here's an example, okay? And it is a selective example. If you take an alkene and you react it with HBr, specifically in the dark, what you end up getting is the 2-bromo product. So it's a secondary bromide. And this is, of course, the Markovnikov product. Okay, but if you take the same alkene with the same HBr and you treat it with a radical initiator like an epoxide, with some light or some heat, you actually end up with very different regioselectivity. So we get a very different reaction because we're doing things under radical conditions versus polar ionic conditions. So that's really nifty. Same reagents, different reactivity, very useful thing to be able to do. So how does this all happen? Well, the first step in any radical process is generation of radicals, and this typically happens through, well, this always happens through some kind of homolytic cleavage. You add some kind of radical initiator, and probably the most common that's used is AIBN. It is certainly not the only one. Now, in this diagram here, we're showing two single-headed arrows, and most commonly in radical chemistry, a lot of people will draw a lot of other arrows as well at the same time. Okay, so those blue arrows show the formation of the double bond and the formation of both radicals. Now, I'm going to analogize the way these reactions run to how we represent normal polar reactions and not draw the backwards headed reactions. Okay, I'm only going to draw the arrows drawn in red, and I am going to assume the blue arrows in future. Okay, now when we're thinking about radical processes, pretty much all of their selectivity and their reactivity is explained by bond strength. It's not everything, but it is one of the most important characteristics we need to consider when we're dealing with a reaction. Weak bonds break easily, strong bonds don't. That's a pretty obvious thing to say. But in addition to that, weak bonds are in the starting materials, and strong bonds are in the products, as a typical example. Now, in order to initiate our radical processes, we usually need a weak bond, such as a peroxide or bromine, and we expose it to something like light or heat, and that generates our radicals. So from radical generation, which is at the initiation step, we then move on to propagation, and the vast majority of a radical is going to be about the propagation. Okay, so on the case of something like benzoyl peroxide, you take the OO bond and it breaks homolytically to give two benzoyl radicals. Now, it is possible, in theory, for the reaction shown here to take place. However, in actual fact, it's relatively unlikely, because what actually ends up happening is that you generate the phenyl radical plus CO2. And then in most cases, it's actually the phenyl radical that does the radical abstraction. Okay, so this is our initiation, and then we have propagation. Okay, so propagation, you essentially start and end with the same radical, either in one or two steps or more. So here we have a relatively weak carbon-carbon pi bond that is reactive, especially when confronted with something like a bromine radical. Okay, Br dot adds to the double bond, and it adds in such a way to give the tertiary radical. Okay, so radicals are stabilized by substitution, like a cation is. Okay, so a tertiary radical is more stable than a primary radical, in the same way that a tertiary cation is more stable than a primary cation. So we take our Br dot, it adds to the double bond to generate a tertiary radical. That tertiary radical can now take an H off of HBr to regenerate our Br dot. The Br dot then goes back to the start and we get our product out. Okay, so that is our propagation step because the Br dot keeps on reappearing, reacting, reappearing, reacting, reappearing. Okay, the termination step in a radical reaction is frankly any two radicals coming together to generate a neutral species from the radical. Okay, so we generate this carbon center radical by hydrogen abstraction. We generate the halide radical from the carbon, and we go around in this circle. Okay, so X dot to C dot to X dot to C dot by shuffling hydrogens all over the place. Okay, that's a very important, very useful thing. Now, the rate of this is pretty much proportional to the strength of the bond that is being cleaved. Okay, so whenever we're generating a radical or we're trying to take off a radical, if we're doing radical bromination, for example, then the strength of the bond is important. So if you look at something like 2-methyl propane here, the central CH bond is actually weaker than one of the bonds here. Okay, the blue radical CH bond, this blue CH bond is approximately 423 kilojoules per mole, i.e. it's like this one, whereas the tertiary one is 397. Okay, so there is a very much a difference in their bond strength. So, as an example, if we take 2-methyl propane and you react it with bromine and light, you end up with T-butyl bromide and actually isobutyl bromide. And you get those in approximately 1-to-1 ratio. Now that doesn't seem very selective, but remember, there is 1 tertiary hydrogen and 9 primary hydrogens. So the tertiary hydrogen is essentially 9 times more reactive than the primary hydrogens, which is actually quite a lot when you consider we're just looking at a very boring carbon skeleton. Okay, so as the bond strength of the hydrogen you're attacking decreases, the rate increases, and as the strength of the bond that you're forming increases, the rate also increases. So again, bond strength is very important for understanding radical reactivity. Okay, and therefore the regioselectivity is dictated not only by the radical stability, but by the bond strength. So let's look at the stability of some radicals. So diazoalkenes, because they generate nitrogen gas, they are relatively unstable. Okay, now the classic one for these diazoalkenes is of course the cyano, because that is our classic initiator AIBN. That one is AIBN. Isobis nitrile. Isobutyronitrile. And you can see that when X is an electron donating group, like a CH3, then the rate goes up by 500 times for the decomposition. If it's a better electron donating group like a methoxy, the rate goes up by 5,000 times. And if you start putting in electron withdrawing groups, well, wow, the rate of reaction, the rate of the decomposition goes up by 100 million to 1 billion times. Okay, 100 million for each of these electron donating groups. And then the phenyl group, astonishingly, is the most reactive of all, which is neither really electron donating or electron withdrawing. That's very weird. So I wonder why that is. Well, we'll tell you. So, how does X stabilize a radical? Well, for a radical that's stabilized by an electron withdrawing group, we're going to draw this molecular orbital diagram here. So that's where X equals Cn or CO2R. So there is a LUMO, a pi star corresponding to this electron withdrawing group. Okay, this is an empty orbital and it's relatively high in energy. Okay. High-ish in energy because it is an antibonding orbital. Okay, so it's higher in energy than a bonding orbital or a non-bonding orbital. The SOMO, the singly occupied molecular orbital of the radical, is non-bonding. Okay, and when the non-bonding SOMO interacts with the LUMO, what ends up happening is that you form a bonding and anti-bonding combination, and we generate a new lower energy SOMO than we had at the start. Okay, the new SOMO is lower in energy than the original one. Okay, so the energy of the radical drops. In actual fact, the energy of the whole system drops, and so therefore overall the radical is stabilized by an electron withdrawing group. Now, almost the exact same thing happens with an electron donating group. It just happens the other way around. Now, I will just say that this lower energy radical, it's low energy, and that makes it electrophilic. Okay, it's willing to accept more electrons into that system. Okay, because we've got space for it. So, how about the electron donating one then? Well, when it's stabilized by an electron donating group, such as an alkoxy group, so the methoxy, say, well, we still have our radical SOMO, and here we have the non-bonding lone pair. The lone pair is on an electron withdrawing atom, so it's nitrogen or oxygen. Oxygen lower in energy than carbon, okay, because it's more electronegative. Simple as that. So we end up mixing our filled lone pair with our SOMO, and we generate a new lower energy HOMO, but a new higher energy SOMO. The key thing here, though, is that 2 times electrons are stabilized, 1 times electron is destabilized. So overall, there is net stabilization by the electron donating group. But the new radical that we've produced is higher in energy, and it is now considered nucleophilic. So depending on whether we stabilize an electron by electron donating or electron withdrawing groups, we can have a very different effect. But the really important thing is that anything that can stabilize an anion or a cation will stabilize a radical. It changes the nature of the radical. It either makes electron donating or electron withdrawing. It either makes it nucleophilic or electrophilic, but it still stabilizes the radical in both cases. Okay, radicals will be stabilized by pretty much anything if they can be. The trick is just trying to understand what that stabilization does to the radical. Okay. So this makes this stabilization, making a radical either nucleophilic or electrophilic, does mean that it can be relatively polar, but they are overall neutral. So they're not an anion or a cation, but they are polar. Okay, so if we look at these two different ways of stabilizing a radical, when you generate a high energy SOMO by reacting it with an electron donating group, these radicals can donate electrons. High energy SOMO equals nucleophilic radical. And of course the reverse is true, and therefore these radicals can accept electrons or electron density. Low energy SOMO gives an electrophilic radical. Okay, easy as that. Well, I hope you find it easy. So, having described these radicals as electrophilic or nucleophilic, why do we care? Well, I absolutely love this example. Consider what happens when you mix vinyl acetate with diethyl fumarate. If you treat this with acid, a mixture of these two with acid, you only get one product. And that product is this polyacetate. How do we get to there? Well, I'm going to do this in red. If I can work out how to make my thing work. Okay, so polyvinyl acetate, H+, lone pair on the acetate, donates, protonates, which gives you this. Now, a second equivalent of polyvinyl of vinyl acetate reacts in an analogous fashion and attacks again, and attacks again, and attacks again, and attacks again. So you can easily polymerize and get through to this acetate polymer. Diethyl fumarate, however, that polymerizes under base. Okay, and base polymerization goes by a slightly different mechanism, which I'll do in green. Whoop. So, base polymerization, well, base or a nucleophile, if you like. Well, that undergoes a conjugate addition to generate the fumarate. A conjugate addition to the fumarate to generate an enolate, but that can then react with a second equivalent of the fumarate. So you do the conjugate addition and it attacks and does a nucleophilic conjugate addition to another molecule, which can then go and do another one and another one and another one. So we just get polymerization under each condition of only one of the species. Using radical chemistry, however, we get an entirely different polymer that I find really cool. So we take our benzoyl peroxide, we photolyze it to get through to 2 equivalents of our carboxyl radical. Let's go for purple. 2 equivalents of our carboxyl radical, which, like we said last time, in actual fact, decarboxylates to give R dot. And that R dot, well, it can do all sorts of things, but for now, we're going to show it attacking the vinyl acetate. Now, acetate is acetyl is an electron withdrawing group, but because the O-acetyl, the acetate, has a lone pair on the oxygen, it counts as an electron donating group, and so therefore we generate a nucleophilic type radical. And nucleophilic type radicals want to react with electrophiles. So our nucleophilic radical does a conjugate type addition to the fumarate to generate a electrophilic radical because it's a radical that's next to an ester. Remember we said that an electron withdrawing group counts as an ester, a nitrile, something else. So we generate then an electrophilic radical, which electrophilic radicals like to react with nucleophiles. So we go round again, and now we generate a nucleophilic radical. So we generate this alternating polymer where we've got electron withdrawing, electron donating, electron withdrawing, electron donating groups. And I think that's absolutely magnificent. We can't do that by any other polar chemical method, but we can do it with incredible control under radical conditions. It's an entirely unique setup compared to what we have normally, which is awesome. Right. So let's do some more radical reactions. So a very useful reaction is allylic or benzylic bromination. It takes a pretty unfunctionalized molecule and does something useful with it. So allylic bromination. What we're going to talk about is the Goldfinger mechanism, discovered by Professor Goldfinger, obviously. So what happens? So when we have the generation of a bromine radical, previously when we had bromine radicals and a primary double bond, we did radical addition to that double bond. When the double bond is more substituted, however, the double bond becomes a bit more hidden, and it isn't the first thing that the radical sees when it's trying to react. Instead, it reacts with the CH bond. So, radical abstracts a hydrogen to generate an allylic radical. The allylic radical is stabilized by conjugation. And that allylic radical can then react with bromine to generate a Br dot radical, which of course goes back. So we can generate allylic bromides from unfunctionalized alkenes. That's neat. Likewise, we can do the same thing with toluene groups. So Br dot gives a stabilized benzyl radical, stabilized through conjugation, which can then react with bromine to generate the Br dot radical, which goes back again. So the key thing is that we want this reaction to have bromine radicals present, but also bromine, molecular bromine, Br2 present. So we want specific conditions that generate some radicals, but not everything being a radical. And the best way to do this is not actually with bromine liquid and a little bit of light, but actually we use N-bromosuccinimide as a steady state source of molecular bromine. Okay, the key thing here is that we're producing HBr as a product of our reaction. So you take NBS, N-bromosuccinimide, and using heat and light, you generate some radicals. Okay, so this is the initiation. Okay, you generate the succinimide radical and the bromine radical, and the bromine radical a little bit can combine with Br with itself to generate Br2, and that becomes important in a minute. So we obviously have a weak NBr bond, which we need to be able to generate radicals. Light and heat breaks it. Typically light is used. Heat is a rare one for this kind of reaction. Once we've generated a little bit of Br2, or more importantly, some HBr, what ends up happening is that the HBr protonates the NBS and generates some Br minus. Br minus then attacks the protonated NBS to generate Br2 and succinimide. This is very similar, I suppose, in some respects to what we did with the Swern reaction when it was warmed up too much. When you start to generate chlorine gas, here we're generating bromine liquid. Okay, so that bromine can then be used as a Br2 source during this allylic bromination. Okay, the reason that this is good is that we only have small quantities of Br2 present at any one time, and so therefore we actually avoid the other reactions that would happen if you just took Br2 and threw it at an alkene. Okay, it's one of the first reactions you learn in organic chemistry is the trans dibromination of an alkene. That's what normally happens in the dark. But with bromine radical generation, you can get this allylic bromination. Alternatively, if you have a real large high quantity of bromine present. Hello? Oh, no, mate. If there is a large quantity of bromine present, then you can end up doing radical addition to the double bond, and that can suddenly become a relatively large product. Okay? So,
John, sorry, yep. I had a question. I don't know if you saw it in the chat.
I did not. No.
Okay. I'll just speak up then. Is there a difference in terms of efficiency of generating the radical when using heat versus light? You said that light has more use, but is there like actually which one's more better kind of thing?
It depends on the reaction to some extent, actually, and it depends on what you're using. In many respects, sometimes you're using both. I like light personally because heat does so very many things. Heat speeds up every reaction, whereas light can be tuned somewhat. Okay, and you can actually use filters on your UV light so that only lets certain wavelengths through. So you can therefore do selective reactions based on that light. So if you tune it essentially to the strength of your bond, you can actually make sure that it reacts with something selectively. So it only initiates some radical reactions, but not others. So, it's kind of like what we do with sunblock, is that is designed to, block out ionizing radiation, but let through other things. So, we end up with a bit of a suntan, but we don't end up with skin cancer. In the same way, you can prevent your reactions having skin cancer by filtering out that dangerous light. And you can be more selective for what reaction you're going for. That makes sense?
Yeah, that does. Thank you. And also,
Yeah.
when you said like heat, what's the usual temperature range that we're looking at for radical generation? Or does
Again,
it also?
depends on the bond.
Okay.
For something like AIBN, I think it's in the high 60s.
Okay.
So Mike's had some problems with this because refluxing THF is right on the borderline for the decomposition of AIBN. But if you go to other solvents, then you have different solubility problems. So light can overcome that. But not everyone has a photolysis kit, whereas everyone has a
oil bath.
or a hot plate.
Okay.
Course, yeah.
All right, that makes sense.
Okay, yeah. Sorry, I did mention in the first lecture that I can't see the chat. So please speak up if you have a question.
Gotcha.
Okay, so let's combine this radical idea with what we were just talking about, the extended enolate. So you can take this, which is obviously ready to be deprotonated by a strong base for extended enolate, but we can do the Goldfinger allylic bromination, and we generate a little bit of Br dot to abstract the gamma hydrogen, and that will then, we can then put the, we can then flow those electrons all the way down to the alpha position where it's going to be most stabilized by the electron withdrawing group. Now remember, this is just a resonance form of this. So it really doesn't matter which one you draw as long as you remember which one reacts. And then it reacts in the terminal position because, again, bond strength is important and you're going to get a more stable product at the bottom, at the gamma position. We can then follow up the allylic bromination. We can follow up the allylic bromination with a Michaelis-Arbusov reaction to generate a phosphonate. And when you have a phosphonate at the gamma position, there is no question as to where the extended enolate will react. It will 100% react at the gamma position because of that additional group. So when you then do an extended Horner-Wadsworth-Emmons, it goes entirely at the extended position, okay? And in this particular case, it actually gives a very high trans-trans ratio in your product, which is nice. So, just a reminder about the Arbusov, like we said, it attacks, does a substitution, the bromide takes off one of the ethyl groups to generate the phosphonate. The phosphonate gets deprotonated by a strong base all the way up, but it is the phosphonate which then defines where it reacts onto the gamma position. We get reversible attack onto the aldehyde, which will then preferentially cyclize when the R and the alkene are trans to each other. So it's fast when trans, or anti, depending on how you want to look at it. And then you eliminate to give the desired product, which could then be useful as a diene for Diels order. So, gamma selectivity in an extended enolate product with the phosphonate present. Okay. So, let's talk about a polar reaction which is useful. Well, we'll discuss it again during other parts of the course, but iodolactonization. Iodolactonization is an interesting one. I2 addition to alkenes is reversible. Okay? In actual fact, it primarily does not add to the double bond. Okay, unlike dibromination or dichlorination, iodine only adds reversibly. Okay, and that is why it's very good for iodolactonization, because the I plus adds to the alkene, but the I minus just sits there. Doesn't react. What happens instead is that we get ring closure to give this product, which is referred to as an iodolactone. Now, it could cyclize in theory at either end of the iodonium, but it selectively forms the 5-membered ring. The 5-ring. And it would form the 6-ring selectively over the 7-ring, for example. But that's great to make an alkene, to make a lactone, but what about if you don't want that iodine? Emergency alert. Tornado warning. Oh, watch out. Okay. So what if you don't want that iodine? Well, this is where you get a very useful reagent, tributyl tin hydride. So this is radical dehalogenation. It's useful for more than just dehalogenation, but this is what we're going to talk about right now. So tributyl tin hydride and a radical that's been initiated from AIBN. Well, CH bonds we know are pretty strong, and they're certainly a lot stronger than tin hydride bonds. And we know that right down here. So we radically abstract the hydrogen from the tin to generate tributyl tin radical. Now, tributyl tin radical, well, that bond, that attacks the iodine because the iodine tin bond is a lot stronger than the carbon tin bond, the carbon iodine bond. My apologies. So we generate tributyl tin iodide as our product, and we have an unstable primary radical. Pretty much the only radicals that are not stable at all are primary ones. Remember, it can be stabilized by either an electron donating or an electron withdrawing group, and primary groups have neither of those things. So this is unstable, and it is reactive. And it is reactive enough, particularly, to be able to take the hydrogen off another tributyl tin hydride to generate another tributyl tin radical, which then re-enters our propagation cycle and gives us our desired lactone. Okay, so real big change, a really useful reaction here. And I say it's really useful because often we're interested in introducing functional groups to a compound, but sometimes you need to get rid of them. And this tin reduction is one of the relatively few methods that can be used to remove a functional group reliably. Now, functional group removal is all very well and good, and Genuinely, really is very good, very useful. But could we actually do something useful with this? That would be nice, wouldn't it? Well, we can take advantage of the different reactivities that are present in this in this radical chemistry to actually do a multi-component reaction. And that, I think, is a really nice way to kind of end up the radical chemistry. So we can use this to actually form a carbon-carbon bond. So we are using 1.1 equivalents of our tributyl tin, and we're using very low equivalents of our AIBN, and we have a acrylate type compound to react with. So we generate tributyl tin radical, okay, as we showed on the previous page. And like we said, the tin and the iodine are a lot happier together than the iodine and the carbon. This generates a radical that is unstable, like we said. Short lifetime and somewhat nucleophilic. Okay, now this radical has the choice of reacting with the acrylate, like I showed you, or it can react with tributyl tin hydride. Well, tin is a metal, and so therefore the tin hydride bond is relatively polarized towards the hydrogen. It itself is somewhat nucleophilic. So if you have a slightly nucleophilic radical and a nucleophilic substrate, those are not going to be as good a match as is a radical acceptor that is electrophilic. So instead of attacking the tin, it attacks the acrylate to generate a new electrophilic radical. And this radical is a lot more stable. This radical is electrophilic. It's going to therefore react with the tin hydride for all the reasons that we said that the primary radical wouldn't selectively. And so we put in our hydrogen here to generate this cyanolactone. It's even possible to use less equivalents of the tributyl tin by actually regenerating it with sodium borohydride. So you take tributyl tin chloride and sodium borohydride, and you actually generate tin hydride. So there are a number of ways where you can keep your tin hydride concentrations low. In this case, we've got a pretty good reactivity match, but we know from the previous page that if there is no acrylate present, then it will just reduce off the tin and put the hydrogen, it will just reduce off the iodine and put the hydrogen onto the methyl group, but it will only do that as a last resort. Okay, so it would rather do this conjugate addition to the acrylate if possible. Okay, so I'm delighted to say that's the end of the radical chemistry. It's a lot of information I've just thrown at you, so sorry about that, but we have a lot to cover. If you've got any questions about it, then I'd be very happy to take them. We've got one final topic. It's not actually very long to discuss before we move on to starting on stereochemistry. This is the end of the regioselectivity and chemoselectivity as a dedicated topic, but we will save that next set of slides, which is our first discussion of a natural product synthesis until Monday next week. So, any questions? Nope. End show. Keep and save. Any questions?